So, hello everyone. We have here a new exercise related to trees, and it's called sametree. Let's check the conditions. So the condition says that we need to design a method that checks if two binary trees are structurally identical and have the exact same node values, such that two binary trees are considered the same if they are structurally identical and their nodes have the same values. So let's say we will need to create a method isSameTree. Like argument, we will send the root of this tree and the root of this tree. So roots of trees which we want to compare, and we will return true if they are identical, otherwise false. So in that example below, you can see that these trees are identical because they have the same structure and same values. If, for example, here we would have, let's say, 4, but here will remain how it is, it will be false, yeah, because the values, the structure is the same, but values are different. And let me show an example. So here we have two trees, this one and this one, and how this algorithm will work when we will implement it. So again, we will start from the root. We will use recursion, and we will start from the roots of this tree and this tree, and we will go to the next one, here also to the next one, and to the last leaf. Yeah, it will be leaf because it will have a null value, and here also. And we will compare, yeah, if value, so null, is equal to null, then in that case we need to return true. We will go back to our root, we will go to the right side, here also, we'll check if null is equal to null. Yes, it is, it will return true. So in the end, we will compare if here from the left side we return true, and if from the right side we have returned also true, then overall result will be true. Yeah, if, for example, let's imagine here we would have let's say 3, but here 4, we would compare 3 with 4, and we will receive false. So it would not be the right answer. So let me show you in dynamically how this algorithm would work. So we start with root 1, and go deep inside our tree. We go to the 2, and we go to the left side in both trees. And now our node from the left in the first tree and node from the left from the second tree are both equal to null, and we compare these values, and because they are equal, we return true. Then we'll return back to our root and go to the right side. Also compare the right node of first tree with right node of the second tree. There we have null, yeah, so you can see that the right node of first tree is equal to null, the same for the second tree. So we compare it with null, and we get true again. And we go back to our root. So now the result is that in let's say in the right side, so we compare the right side of the first root and the right side of the second root, they are equal. Also, we have done the same for the right sides of both trees, and they are also equal. So now we just return true, yeah, because both sides are equal. So the left side of the first and second tree is equal, and the right side of the tree are also equal, so overall result is true. But in case if, for example, only let's say left side of first and second tree would be equal, it would return true. But let's imagine that right side of the first and second tree would be different. Yeah, it would return false. And in that case, we would get false because we have one true and one false, and the result is false. Yeah, because one of the sides is not equal, but we need to have all sides to be equal for that task. In our case, both sides are equal, so we return true. And then we return to the first root of our trees and do the same operation for the right side. And in the end, here we will get that the right side is equal, so it will return true. The left side. The right side also will return true because this subarray is equal to this subarray. And then we will compare if this if the right side is true and the left side is true, then these trees are equal, so they have the same structure and the same values, so we consider it like same trees. In our case, we will get false. So that's the idea of the algorithm, how it will work. So now let's proceed and check how we can implement this algorithm. So let's implement this method. Again, like always in all my videos, I really suggest to watch previous videos because they are related to tasks which I resolve in the current video, and it would help you better understand what actually I'm doing. But okay, so let's continue. Let's implement our method. So it will be public static, and let's call it is same tree. And here, like argument, yes, also we'll need to put here boolean because we want to return a boolean. Our method will say us if trees are equal or not, and in that case we need to return boolean. So we will have here two arguments, where both arguments will point to the root of the trees which we want to compare. So let's do it. Tree node, let's say first root and second root. Okay, perfect. In this solution, I will use recursion, and in that case, first of all, which I suggest you to think about is what will be the condition for the last iteration for that recursion, because if we will not have this condition, then the recursion will execute infinitive times, and we don't want to do that because we will need to stop it. And what will be the condition? So when we will reach the last node, so when we will reach the leaf, yeah, and if we will not throw any, if we will not return false, which will mean that some nodes are not equal, it means that we went through all nodes and they all are equal, so that means that we can return true. So let's put here this condition. So if first root is equal to null, and if second root also is equal to null, Yeah, so in that case, we can return true. Yeah, so it will say that we reached the last node for both trees. Actually, here I have next the first. Yeah, why we can do something like that? Because in that case, it will mean that, yeah, till that moment, all nodes are equal, but it would be a possibility that, for example, second node has more nodes, and in that case, this condition would be not correct. So we need to reach the last node for both trees, and only in that case we will be sure that all nodes was validated and all of them are equal, so we can return we can return true. Now let's put this condition, so when trees are not equal. And trees are not equal in case if some of them, if one, for example, is equal to true. So let's say first root is equal to true, or to null, I'm sorry. Or if another is equal to null. Or if they are not equal. So first root is not equal to second root. Yeah. Okay. So what does it mean? It means, let's imagine that you have two trees and one node, which now you compare. Let's imagine first node is equal to null, but the second one is equal to 2. Yeah, and in that case, trees are not equal because nodes are not equal. Or it may be a situation that, yeah, nodes are both present, but they just are not equal. So for example, one is equal to 2, but another is equal to 3. Then in that case, trees are also not equal. And let's return false. Perfect. And now we will need to call recursively our method is same tree for left part of a tree, so of the trees, and for right side of trees. And if the left sides of trees are equal, and if right sides of trees are equal, then in that case, here we will have true, here we will have also true and true is equal to true, and only in that case we will return true. So that's the solution. I hope it was helpful. And now let's check the complexity. So the time complexity for this algorithm is ON, but space complexity is OH. So I hope we will see in the next video, and I hope everything was clear. If you have any question, please write them in the comments and I will try to help you, or maybe someone else will help you. And we will see in the next video. Bye. So when I was watching the video, I have noticed that here I have committed a mistake because here we need to compare values but not pointers. Yeah, and for that we need to put here also value. So that was the mistake. I hope you have noticed that. If not, that's the correct solution. So you will see. Bye.